The next data structure we're going to cover is a stack, or a last in, first out collection. Imagine you have a tennis ball case, right? And you fill it up one at a time because there's only a single opening. Right? Now your tennis ball case is full. If you want to access tennis ball 2, you would have to remove the top tennis ball one at a time iteratively, right? So I would remove tennis ball 4 and tennis ball 3, and now I would have access to tennis ball 2. This is how a stack data structure acts. Items must be inserted and removed from the same end. The last in, first out behavior is incredibly useful in real life. For example, you could use it to implement an undo function for a text editor. There are typically 4 operations associated with a stack: push, pop, peek, and isEmpty. For push, we insert an element to the stack and we have a time complexity of big O of 1, so it's a constant time complexity. For pop, we remove the top element from the stack, and again the time complexity is constant. For peek, we are simply returning the top element from the stack, and once again it's a constant time complexity. For isEmpty, you're simply checking if your stack is empty, and once again that's a constant time complexity. For a constant time complexity, that's saying no matter how big the stack is, whether it's 1 item or 1 million items, the operation is going to take the same amount of time to complete regardless of the size of the input. That's what constant time means. One way that we could implement a stack is through the use of an array. And if we have an array, we have a fixed size. In this situation, we have an array of capacity 3, and that means we can at most hold 3 elements in our stack. Another thing that we're going to be using alongside the array is top. Top is going to point to the current index that we're at. Right now, it's pointing to -1, indicating we don't have anything inside of our stack. All right, if we wanted to push X, we would update top to point to index 0, and we would push X. If we wanted to push Y, again, update top to the next index, and now we can have Y. If we wanted to push Z, we would once again update top, have it push to the next index, and we could have Z. If we wanted to do peek, we would look at what top is pointing to. It's pointing to index 2, and we have Z there. So it would return Z. If we did a pop operation, that would delete Z and decrement top. Right? So if you did peek now, we would be at index 1, which is holding not Z, it's holding Y. Right? And we could do 2 more pop operations, pop and pop. So we would delete Y, decrement top to 0, then remove X, and then finally decrement top one more time back to -1. At a fixed sized stack implementation using an array. So we have the stack class. Within it we have the init constructor. we're going to pass in a parameter capacity. This is going to help us set up our array with that specified capacity. We're going to initialize top to be at -1, so we're outside any valid index, and we're going to keep track of the capacity of our stack using this variable. For the push method, we are going to pass in a parameter n. This is going to be used to push that value into our stack. This is the value that we want to push, right? If our stack is full, raise an exception, otherwise increment top and set the value n at index top. For the pop method, if our stack is empty, raise an exception. Otherwise, save the value that's currently at index top, because once we decrement top, we no longer care about that value. We treat it as if it's been deleted. We decrement top, and then finally we return the value that we previously stored. For peak, check if the stack is empty. If so, raise an exception. Otherwise, return the value that's currently at top. For our empty method, we're simply checking, is top at -1? Is it outside any valid index? For is full, we're checking if top is at the capacity -1, because if you have a capacity of 4, the last valid index would be 3 if you're using zero-based indexing. The previous implementation using an array is good, but it does have the limitation of having a fixed size. How do you deal with this? Well, you could do a dynamic size implementation using linked lists. So imagine we start off with an empty linked list. Head is pointing at null. We want to push into the stack X. So what would we do? We would create this new node, fill the data with X, and then the next pointer would point to the current first node in the sequence. In this situation, it's actually just pointing to null, right? You would update head to point to our new node. I'm going to clean this up a little bit. So we're pointing to X, and this is pointing to null. We want to try again, push Y. So we create a new node, fill the data with Y. We set the next pointer to be the current first node in the sequence. In this case, it's X. We update head to point to our new node. We try once again. Push Z. Create this new node. Fill data with Z. Set the next pointer to be the current first node in the sequence. That's Y. Update head to point to our current, or our new node, which is Z. What happens if we do peak? Well, we can see that head is pointing to the first node in our sequence, it has a value of z, so depending on your implementation, it could simply return z. What about if we do pop? Once again, we go to head, we see that the first node in the sequence is z. We're going to store that value, right? We are then going to go to the next node in the sequence that z is pointing to. It's y. So what are we going to do? We're going to update head to point to that node. And then for our purposes, we could treat node z as if it's been deleted, and then you would return z and do whatever you want with that value. Let's try it again. We do pop. We go head. It's currently pointing at the first node in the sequence, which is y. We are going to store that value, y. We look at the next node that y is pointing to. That's x. We are going to update head to point to that node. And then for our purposes, the y node no longer exists, and we can return the y value because we have it stored. This implementation is great. It allows you to input as many nodes into the stack as you would like. However, you do have the issue of it taking up more memory space when comparing one node in the linked list versus one element in the array. Let's look at the implementation for a dynamic size stack using linked lists. We have a class called node, taken value, that initializes the data for the node, and we have next as our pointer. For the stack class, we have a constructor. Head is going to point to the first node in the sequence. It's currently pointing to none or null. This is at initialization, meaning that our linked list is empty at the start. For our push method, we are getting in the parameter n. This is the value that we're trying to push into our stack. So create a new node, initialize data as n, set the next node after new node to be what we currently have as the first node in the sequence. Update head to be pointing at the new node. For our pop method, check if the linked list is empty. If it is, raise an exception. Otherwise, save the current top value, right? The first node in the sequence, get the data or value from there. Then update head to be not the first node in the sequence, but the second node in the sequence, right? Finally, return top value. For peak, check if the linked list is empty. If it is, raise an exception. Otherwise, return the value of the first node in the sequence. Check if your linked list is empty. See if head is equal to null. Being able to implement your own stack from scratch is great, but many programming languages have their own stack implemented. So in Python, this is how you would use it. If you wanted to initialize your stack, you would initialize it using a list like this. The push method, its equivalent is the append method. So here we are appending 10 to the stack, then 20, then 30. If you want to peek, look at the top value in your stack, you would simply go to index -1. This is the most recent index in your stack. If you wanted to pop, it would actually be the same method. It's called pop. Over here, I am saving it to popped top. If you wanted to check if your stack was empty, you would check, is the length of the stack equal to 0? And that's a wrap on stacks. So just as a checklist to see everything that we should be able to answer after this video, we should be able to describe a stack, also known as a last in, first out collection, and its operations. We should be able to implement a fixed size stack using an array. We should be able to implement a dynamic size stack using a linked list. We should be able to compare the trade-offs between an array and a linked list implementation, as well as understand the time complexity for the operations of a stack. Alright, in the next video we'll cover queues.